All right. So today we're going to do the Exam 4 review for Dr. Kelley's 1211 class. We're going to cover chapters 7 and 8, and we're going to work through the problems that Dr. Kelley gave me to review. We have 5 priority A problems, 1, 2, 3 priority B problems. So we'll just get started. If you have any questions, just type them in the chat window, and we'll go through it. Okay, first problem here has to do with calculating delta H from bond energies. So there's several different ways of calculating delta H. This is just one of them. So let's write this equation down. H2O2 plus CH3OH goes to H2CO plus 2H2O. Okay, now the idea of determining the enthalpy by bond energies is the realization that the delta H is basically going to be the sum of the bonds broken in the reactants minus the sum of the bonds formed in the products. So one way to look at this is we're going to put energy in, and we're going to break up the bonds in the H2O2 and the CH3OH. And then we're going to recombine those atoms and get the energy released by forming the bonds in the H2CO and the 2 waters. Okay, so this is sort of a generic equation, but now let's get really specific. Let's rewrite these because to count the bonds, we need to know what the structures are. So let's redraw these, showing what the bonding arrangement is. H2O2 is actually HOOH. The CH3OH looks like this. The H2CO, now this is tricky. This is an issue here. If we look over here in the bond energies, there's 2 values listed for CO bond energies. One is for a double bond, one's for a single bond. So I won't go through all the details of the Lewis structure, but that is the structure of H2CO. And then, of course, water looks like this. So now all we need to do is start counting these bonds. So the delta H will be, we're going to break 1 OO bond. We're going to break 2 OH bonds. We're going to break 1, 2, 3 CH bonds. And that really, we have to keep going. We're going to break 1 C single bond O bond. And for the last one, we're going to break 1 OH bond. So after we've gotten all those will be the bonds broken in the reactants. Let's go ahead and plug in the values. So the OO bond is 146. So let's just put that in, 146. Now, look, we are breaking 2 OH bonds over here and another 1 OH bond. So let's combine these to be 3 OH bonds. So that would be 3 times OH. OH is 463. CH bonds are 413. The C double bond O. So the CO bond is 358. And if we do all that multiplication in addition, we get 3132, and these will be kilojoules. So that is the energy necessary to break the bonds in the reactants. Okay, now we're going to subtract the bonds formed in the products. So what are we going to do? So we're going to form 2 CH bonds right here. We're going to form 1 C double bond O. And then when we get to the waters, each water molecule has 2 OH bonds, but we're forming 2 moles of water, so that will be 4 OH bonds. Plugging in the values, that's going to be 2 times 413. That's a CH bond, is 413. The C double bond O is 799. So that was the right one we had to pick. And OH bonds are each worth 463. So if we tally those all up, it's minus 3477 kilojoules. So the delta H would be the 3132 kilojoules on the positive side minus 3477 kilojoules for an overall enthalpy of minus 345 kilojoules. Okay. So that was a little bit involved, but not too bad. In your book, this concept is covered on page 323. So if you want to go a little deeper into that, maybe you can go back and review it. Okay, so if you have any questions, just let me know at any point. Otherwise, I'm just going to keep on going. Okay, number 2, calculations with lambda, nu, and E. Okay, see, these are going to be energies of different events. Before we start working the problems, let's just review some of the key equations. So the energy of a certain wavelength or frequency is given by h nu. The other thing that's true is the wavelength of an energy times the frequency of that energy equals the speed of light. So also, we can also rearrange. And just to be clear, h is a constant. That's called Planck's constant. Let's just write its value down here. 6.626 times 10 to the minus 34 joules seconds. C is also a constant. That's the speed of light. 3.00 times 10 to the 8th meters per second. Okay, so there's 2 problems that we're going to work. What is the energy of a photon of blue-white that has a wavelength of 453 nanometers? I see we've got a few others that have joined, so we're going to keep going. And we've already worked problem 1, so you see the workout here. And we're on to problem 2, so you got here close to the beginning. Okay, we're going to be working problem 2, which is an A problem and a B problem dealing with energies of a certain wavelength or frequency. Okay, so the question asks, what is the energy of a photon with blue light which has a wavelength of 453 nanometers? Well, we said that energy is h nu. Now, when they say the wavelength is 453, wavelength is given by lambda. So how about we'll plug in C over lambda for nu. So this would give us h hc over lambda. And let's just go and plug in these values. Planck's constant is 6.626 times 10 to the minus 34 joule seconds. C is the speed of light, 3.00 times 10 to the 8th meters per second. Now the wavelength is given as 453 nanometers. Okay, so let's think of that. The wavelength is 453 nanometers. Now a nanometer is a 10 to the minus 9th meter. And if we were to put that in proper form, that would be 4.53 times 10 to the minus 7th meters. So since we have meters per second, let's use meters. So 4.53 times 10 to the minus 7 meters. So multiplying and dividing, we get 1.15, 1.18 times 10 to the 15th. Okay, now let's figure out the units. So we have joule seconds in the numerator. So the seconds would cancel with reciprocal seconds. The meters in the numerator will cancel with meters in the denominator. So the answer will just be joules. And that's good, because joules is a measure of energy. So that is the energy associated with that blue light. Okay, let's go to the B. So this was A, B. B says, in the hydrogen spectrum, what is the wavelength of light? So lambda is going to be our unknown, associated with the, a line in the, I'm sorry, I skipped. A line in the spectrum of atomic mercury has a wavelength of 254 nanometers. What is the frequency of this light? Well, if we look at our relationships, they're not asking us anything about energy. They're asking us for the relationship between wavelength and frequency. So frequency is speed of light over lambda. So all we need to do is plug in speed of light, 3.00 times 10 to the 8th meters per second. The 254 nanometers, similar to what we did here, would be 2.54 times 10 to the minus 7 meters. So the units would be meters canceling with meters. So the frequency doing that division is 1.18 times 10 to the 15th seconds to the minus 1. And seconds to the minus 1 is the unit of frequency. And sometimes you'll see that stated as hertz. 1 hertz is the same thing as 1 reciprocal second. Okay. All right. So we're done with the first two. Like I say, anytime, just shoot me a question. Otherwise, I'm going to just keep on going along. Okay, hydrogen line spectrum and calculations, chapter 7. Okay, and this topic is covered on page 265 in your book, but let me just summarize it here. In the hydrogen spectrum, what is the wavelength of light associated with the n equal 3 to n equal 1 electron transition? Is energy being absorbed or released? Okay, so let's start off. So we want the n equal 3 going to n equal 1 energy. Okay, now let's, I don't have the page to refer to, so let's draw a little diagram that sort of represents these energy levels in the hydrogen spectrum. The energy levels are dictated by the quantum levels, n equal 1, n equal 2, n equal 3, and etc. n equal 4 and going on up. So in this particular problem, they're asking us for the energy of the 3 to 1 transition. So they're asking us, what is the magnitude of that transition? Okay, if we look on page 263, it gives us the relationship where we can calculate that. Delta E, and that delta E represents the transition between two different energy levels, is minus 2.178 times 10 to the minus 18th joules times 1 over NF, where NF is the final level, and this is squared, minus 1 over Ni squared. Okay, so let's look at that. So NF in this case will be the n equal 1. And I is the initial energy state, which is going to be 3. So let's just keep going. Minus 2.178 times 10 to the minus 18th joules. Okay, 1 over NF squared is going to be 1 over 1 squared. 1 over Ni squared is going to be 1 over 3 squared. Okay, so that math is has gotten pretty simple right now. So minus 2.178 times 10 to the minus 18th joules. Okay, 1 over 1 squared is 1, so we'll just call that 1. 1 over 3 squared is 1 over 9, which is 0.111. So just do that subtraction, multiply, and we get minus 1.936 times 10 to the minus 18th joules. So that's the magnitude of the energy. Now what they asked was, is energy being absorbed or released? So if we think about it, we're starting from a high energy state at n equals 3, and the electron is going down in energy to n equal 1. That means that energy is being released. All right. Okay, so are we good with that? I'll maybe give you, oh wait, I didn't spell energy right. Okay. So I'll give you a second to kind of take a look at that. All right. Okay, let's see where we are. Okay, quantum numbers and electronic configuration. So as I did in the last review, I'll work the odd problems because they have the answers in the back of the book. Okay, so we're going to get into your textbook, chapter 7, and we're going to start with problem 101. Okay. All right, so let me try to summarize that problem here. So this is going to be number 4, which is going to be problem 7.101 in your book. And let me just try to summarize what the problem is asking. It says, give a possible set of values for the 4 quantum numbers for all the electrons in a boron atom and a nitrogen atom if each is in the ground state. Okay, so what they want is the 4 quantum numbers for all the electrons in a boron and B, nitrogen. So we'll work these two problems separately. Let's just get into the boron problem, and then we'll move on and do the same thing on the hydrogen problem. Okay, All right. So let's do a quick review on what are the 4 quantum numbers. So recall we have the n quantum number, which is the same as what we just talked about. You know, n are integers, 1, 2, 3, 4, etc. The next quantum number is L. L goes from 0 up to n minus 1. The third quantum number is m sub L, and that ranges in integer values from minus L through 0 up to plus L. And the fourth quantum number is m sub S, an electron spin. It's given values of either plus a half or minus a half. All right. Now let's look at boron. Boron has 5 electrons. Look it up on the periodic table, atomic number 5. And its configuration would be 1s2, can't figure out how to get rid of that. We're going to ignore it. 1s2, 2s2, 2p1. Now, if you look at that in another representation, sometimes we show the box diagram representing the orbitals. Remember, s orbitals occur 1 at a time, and p orbitals occur 3 at a time. So when we say we have 2 electrons in a 1s orbital, we have 1 with spin up, 1 with spin down. Same in the 2s orbital, 1 up, 1 down. And when we get to the p orbital, we have 1 with spin up. So let's try to put this in like a little chart form where we're going to get the 4 quantum numbers, n, L, m sub L, and m sub S. And let's list out these electrons. We have 1s2, so let's list 1s twice. We have 2s electrons. Let's list 2s twice. Each row is going to represent the 4 quantum numbers for that 1 electron. And then we have 1 2p electron. Now, one of the rules of quantum numbers is that no 2 electrons can have the identical 4 quantum numbers. It can have 3 that are the same, but it cannot have 4 that are the same. So when we fill in this table, we have to make sure we have that figured out. Okay, so for a 1s electron, what is the n value? Well, the n value is given by the first number, so it's n equal 1. Okay, what is the L value? Well, L goes from 0 up to n minus 1. Well, if n is 1, the only L that's possible is 0. What is m sub L? Goes from minus L to plus L. Well, the only possibility there is 0. And m sub S could be plus a half or minus a half. So we'll give this one plus a half. For the other 1s electron, the n, L, and m sub L will be the same, but the m sub S will be minus a half. Okay, so these now have taken care of the 1s2 electrons. Now let's move on to the 2s electrons. Okay, it's going to look similar, but the big difference of course, is the 2. That means n is 2. L is again 0, m sub L again 0, m sub S plus a half, and minus a half. So this represents the 2s2. Okay, now the 2p electron. Again, it's n equal 2. Now, what is a p electron? A p is going to be L of 1. Remember, L can go from 0 to n minus 1. If n is 2, 2 minus 1 is 1. Okay, the m sub L goes from minus L to plus L. There are 3 m sub L possibilities, minus 1, 0, and plus 1. And I can just label them. We'll call this one minus 1, 0, and plus 1. Frankly, it's arbitrary, but they're just asking for one possibility. So we'll put minus 1 there, and we'll put the plus 1/2 there. Okay, so as you can see, we've identified the possible 4 quantum numbers for the 5 electrons. Every one of these sets is unique, and it's a systematic way of looking at it. Okay, I don't see any questions yet, so now we'll go on to the nitrogen. Okay, nitrogen. What is the situation with nitrogen? Well, that is atomic number 7, so it has 7 electrons. So its configuration is 1s2, 2s2, 2p3. Okay. If we were to show this in the box notation, the 1s2 and the 2s2 will be the same as it was in boron. Now, when we get to the 2p, we come to a situation where there's a certain rule. We have 3 electrons to put in these 3 boxes. How are they to be arranged? They follow a rule that's called Hund's rule, which says is that electrons go into p orbitals one at a time with the same spin. And you can look up in your textbook a little more detail on Hund's rule, but that will be it. Okay, so let's set up the same matrix, and we're going to talk about all 7 electrons. So we're going to go with our N, our L, our M sub L, and our M sub S. And that will be the 4 quantum numbers we're going to identify. So we have 2 1s electrons, just like we did in boron. We have 2 2s electrons, just like we did. And now we're going to have 3 2p electrons. So we're going to write down 2p 3 times. Okay, the 1s and the 2s, we're just going to replicate what we had for boron because it's really the same. So let me just jot this down for completeness. Okay, now let's get to the 2p orbital. All right, so for every 2p orbital, n is 2. For every p orbital, L is 1, just like it was in boron. Now remember, I said before that the M sub L values are going to be -1, 0, and +1. In the boron atom, there was only 1 2p electron, so we picked the -1. In this case, we have 3 2p electrons, each in a different 2p orbital. So the M sub L values will be -1, 0, and +1. Now we said that in that 2p array, all the electrons are going to have the same spin. So they're all going to be +0.5, +0.5, +0.5. The difference in the 3 2p electrons are the M sub L values. All right. Okay, let me again take a second and let that sink in. See if that makes sense. If you have any questions. All right. Okay, so that was problem 101. There's a second problem listed, problem 89. If we go up to the question list, that's over here. Problem 89. Let's see what that asks us to do. So let me get my notes. Okay. Problem 89. Okay. Okay, again, let me just try to summarize. It's a very simple problem that they're asking. So problem 89 from your textbook says Draw atomic orbital diagrams representing the ground state electron configuration for each of the following elements. A, we're going to work sodium. B will be cobalt, and C will be krypton. Okay, so they want the atomic orbital diagrams representing the ground state. So we're going to write that out, and they also, so they want the orbital diagram plus they want to know how many unpaired electrons are there in that configuration. Okay, so what they're asking, let's go back to our nitrogen example. How many unpaired electrons were there in nitrogen? Well, if you look at it, we have 1, 2, 3, 4, 5 with spin of +0.5, and we have 1, 2 with spin -0.5. So we actually have 3 unpaired spins. Now that problem didn't ask for the unpaired spins, but that's the way we're going to attack this with the 3 examples we're going to work here. Okay, so let's go through this. So let's start with sodium in a manner just like we did before. Sodium is element 11, has 11 electrons. So let's put the configuration together similar to what we did with the nitrogen and boron. Let's draw out the configuration. 1s2, 2s2, 2p6, and that gives us 10 electrons. The next orbital would be 3s1. Okay, doing the box notation, whoops. 1s, 2, 1 spin up, 1 spin down, 2p6. Again, p orbitals come 3 at a time, but if there's 6 electrons, they're completely filled. Each orbital has 1 spin up, 1 spin down. And then the 3s orbital has just the 1 electron spin up. So if we look at it, any filled orbital, this is going to be a general rule, any orbital that is completely full will have no unpaired spins. So this is the only orbital which is partially filled, and this would give us 1 unpaired spin. Okay, let's move on to cobalt. Cobalt is element 27, and I'm going to assume that you understand the ordering of the orbitals. Just to go through the rules for the maximum occupancy, maximum electrons, an s orbital, it doesn't matter if it's 1s, 2s, 3s, can hold at most 2 electrons. P orbitals come 3 at a time. The maximum occupancy would be 6. D orbitals come 5 at a time. The maximum they can hold is 10. And I don't think we're going to go beyond that. There are f orbitals, but since we're not going to cover that in any problems today, let's leave that for now. Okay, so what is going to be the configuration? Cobalt, 1s2, 2s2, 2p6. At that point, we have 10. Moving on, we have 3s, which holds 2. We have 3p, which holds 6. The next orbital is the 4s orbital, which holds 2. Now, at this point, we have 10, 20. We have only 7 electrons left over. and the next orbital that will be filled is a 3d. It can hold at most 10 electrons, but we only need 7 to give us our grand total of 27. So if we fill in the boxes, it's going to look very similar. All these lower orbitals are filled. The 4s orbital is filled. Now, 3d orbital, this is where it gets interesting. There are 5 orbitals in the d set. Now, we talked about Hund's rule a minute ago, which said that as we put electrons into that d orbital set, they're going to go in one at a time, spin up. So let's start off by putting 5 electrons all spin up. Now we need to go back and add 2 more. Then we'll start pairing up. So the d orbital set would look something like that. Now, all these lower orbitals are filled, so that means there's no unpaired electrons. The first 2 orbitals in the d set are paired, so there's not going to be any unpaired spin. But these last 3 are not paired, so we're going to get 3 unpaired spins from cobalt. Okay, last one, krypton. Krypton is over there in group 8. It has 36 electrons. So let's just go on. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. If we add up where we are, we have 10, we have 20, we have 30 at this point. The next orbital in line is 4p, and we know 4p can hold at the most 6 electrons, and that's what we need. We need to put 4p6. So, let's just, for completeness, fill in these boxes. We've seen this a couple of times, so I'm just going to go through it quickly. For S2, the 3D set, all 5 of those orbitals are completely filled, 10 electrons. So there's going to be a spin up, a spin down in every one of those 5D orbitals. And now here we are at the 4p. It's the highest energy orbital, and it has 6. And we've seen every time we have a p6, all those electrons are paired. So there are 0 unpaired spins in the argon atom. All right. So that was a lot of work, but I think there was a lot of similarity between the 3 problems. Okay. Okay, so we're making good progress. We've done, I think, 1, 2, 3, 4. Okay, the last problem is Vsepr and Polarity. The problems shown are 121 to 124. So we'll work the odd problems, the 121 and the 124. So now we're going to take a plunge into Vsepr. Okay, let me get my notes here. Okay, so problem 5. Let's start with in chapter 8, problem 121. And what it wants is us to evaluate chapter 8, problem 121 is predict the molecular structure for each of the following. So let's list these molecules. I'm going to work them all, and you'll see why in a minute. There's going to be a pattern that forms. Tellurium Tetrafluoride, the last one is Phosphorus, Cl5. Now, I'm not sure everyone is completely up to speed on Vsepr, so I'm just going to take a couple of minutes to review how do we build the Lewis structures. How do we determine the molecular shapes? So let's just review for a second how we go about building Lewis structures and determining shapes. Okay. So to get the Lewis structure, okay, we have a pretty generic process that works for every molecule you can come at. The first step is to count all the valence electrons. Secondly, select the center atom and this will be the element that has the lowest electronegativity. Thirdly, connect outer atoms to the central atom with a single bond. Fourth, add electrons to the outer atoms to satisfy the octet rule. Satisfy octet. Fifth, if we have any electrons left over, add remaining to the center atom. And the last one is, if needed, create multiple bonds to satisfy octet on center atom. Okay, at this point we will have our Lewis structure in hand, and the next thing we'll do is determine its shape. And what we say by shape is we talk about the electronic geometry, and this is the way the electrons are arranged in space, and then also the molecular geometry, which talks about where the atoms are arranged in space. So to get the structures, electronic and molecular structures, we refer to the Lewis structure, and A, we count how many, the number of atoms bonded to the center atom. I'm just going to call it Ca, center atom. And we're going to call this parameter B. Secondly, we're going to count how many lone pairs are on the center atom. And we're going to call this L for lone pair. And then we're going to define something called the steric number. We'll abbreviate it SN. And that is simply going to be the sum of the B plus the L. So that's very generic at this point, but we will then work the examples and it'll become a little more clear. From the steric number and the bonding and the lone pairs, we will get the electronic geometry and the molecular shape. Okay, so that's sort of a little background. You might already know that, but I just wanted to get everyone up to speed, and now we can dive in and work these molecules. What I'm going to suggest is let's start with the PCl first and work our way backwards. You'll see why in a minute. Okay, so PCl5. Okay, the first one says count all the valence electrons. Well, phosphorus is in group 5, and remember, the group number will represent the number of valence electrons. We have 5 chlorine atoms. Chlorine is in group 7, so each chlorine brings 7 valence electrons, so that's going to be a total of 35. We're going to add the 5 and the 35, so there are 40 electrons in the molecule. Okay, what's next? Select the center atom. So if you recall the relationships on electronegativity, phosphorus is to the left of chlorine, it's lower electronegativity. So it's going to have, it's going to be the center atom. Let's see, where should I draw this? Let me draw it here. Connect the outer atoms to the center atom. So the 5 chlorines will be attached to the phosphorus. Now, at this point, you don't have to necessarily reflect the actual reality of the structure, because frankly, at this stage, we don't know what it is. But we're just trying to get a good representation of how the atoms and electrons are arranged. After we've added those 5 chlorines with a single bond, each single bond is represented by 2 electrons. So the 5 bonds that we've written account for 10 electrons, which means we have 30 electrons left over. The fourth step says add electrons to the outer atoms to satisfy their octet. So if we look at any of these chlorines, the electrons which are shared between the chlorine and the phosphorus are counted on both atoms. So at this point, with the single bond, we already have 2 electrons on the chlorine. The octet means it has to have 8 electrons. So the difference is we need to add 6 electrons from this 30 electron group to fill the octet on chlorine. And every chlorine is the same. So we're going to give each chlorine 6 electrons. So each chlorine got 6 electrons. There's 5 chlorines in the molecule. 5 times 6 is 30. So we have no electrons left over. It says, Rule 5 says, add remaining electron to the center atom. Well, we don't have any. 6 says, if needed, create multiple bonds to satisfy the octet on the center atom. Well, right now, phosphorus has 2, 4, 6, 8, 10. It actually has more than the octet. And there is an exception to the rule which says if an element is in the 3rd or 4th or 5th row, it can have more than 8 electrons on it, but we don't need to add any electrons to the center atom. So this is the Lewis structure of PCl5. Okay, now let's do our counting. B, the number of bonds which are connected from outer atoms to the center atom. Well, there's 5 of them. How many lone pairs are there on the center atom? There's none. There's a lot of lone pairs on the outer atoms, but we're only interested in the phosphorus, and that has none. So the steric number is going to be 5. And this is going to define an electronic geometry. And I've added here a table that we've used before, and you'll see here is steric number 5. The generic electronic structure is called Trigonal Bipyramid. Okay. So we have an electronic geometry of trigonal bipyramid. Now, what about the molecular shape? Well, the molecular shape is going to be the same thing. When we have an atom in every position, the shape of the atoms is actually going to be also trigonal bipyramid. Okay. Now, it also wanted to ask, what are the angles? So here you can see there's 2 different types of angles. One is going to be a 90-degree angle, and one is going to be a 120-degree angle. Let me try to draw a trigonal bipyramid a little differently. So what we really have is a triangle in the plane, which is flat. So the angle between the phosphorus and the chlorines is going to be 120 degrees. And then we have what we call axial positions, which you could call it the North Pole and the South Pole. And the angle between them is going to be 180 degrees. So this is an unusual geometry because there are actually 2 different angles that represent the structure. Okay, so that's PCl5. Okay, so that was the first one. The second one they asked us to work was tellurium. Let's see, where is it up here? Tellurium Tetrafluoride, TeF4. Okay, so we can follow the exact same process. We could probably go a little faster. So tellurium, where is tellurium on the periodic table? Well, if you look in group 6A, starting with oxygen, it goes oxygen, sulfur, selenium, tellurium. So tellurium is in group 6, so it will bring 6 valence electrons. The 4 fluorines, fluorine is also in group 7, so the 4 fluorines will bring 28 altogether. So this molecule is going to have 34 electrons. As before, the tellurium will be in the center, and the fluorines are going to be around the periphery, the outer atoms. The single bond between the fluorine and tellurium, again, is 2 electrons. We have 4 single bonds. 4 times 2 is 8. So we have 26 electrons left to place on the outer atoms. As in the case of the chlorines, we need to put them on the fluorines 6 at a time. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So to accommodate the octets on the 4 fluorine atoms, we had to use 4 times 4, or 6 times 4, 6 times 4, which is 24 electrons, which means we have 2 left over. Now, if we go back up to our rules, it says, Rule 5 says, add remaining electrons to the center atom. Well, in the case of the PCl5, we didn't have any electrons left over. Now we do. So these 2 electrons are going to go as a lone pair on the tellurium atom. Okay. If we look at the center atom, we have, once again, 10 electrons, so there's no need for multiple bonds. Now let's get into our B and our L. The bonding number is going to be represented by the 4 fluorine tellurium bonds. So we have 4 of those. We have 1 lone pair on the tellurium, so it's 1. So the steric number is again 5, but it's achieved in a different manner. Now, any molecule that has a steric number of 5 has an electronic geometry, which is trigonal bipyramid. But because it has only 4 fluorines and a lone pair, the molecular shape is going to be different. So let's look into this chart. And what we see is we're right here. The green balls are represented by the fluorines. And one of the rules we have in trigonal bipyramid is that lone pairs go into the equatorial position, into the triangle in the plane. So you can see that third position in the triangle is occupied by a lone pair. So this is called the sawhorse structure. You know, hopefully you may have had a chance to work with some molecular models, balls and sticks, and it might be a good idea to construct that one to see where the sawhorse comes from. So molecular shape is sawhorse. Okay. All right, so that's tellurium tetrafluoride. Okay, let's move on to the next one. What is next is ICl3. Okay, ICl3. That looks odd in a way because all of the elements are from group 7, but we're just going to follow the rule. The iodine is group 7, so it brings 7. The 3 fluorines are also each going to bring 7. 3 times 7 is 21. So it's going to be a 28 electron molecule. Now, everything is in group 7, so which of these is going to be the center atom? Recall, electronegativity decreases going down a column. So chlorine is higher in group 8. Iodine is lower, so iodine will be the center atom. So we're going to put the 3 chlorines around. For the 3 bonds, we have 6 electrons. We have 22 electrons left over. Put them 6 at a time on the 3 chlorines. 3 times 6 is 18. We now have 4 left over. And those 4 electrons will go on the center atom as 2 pairs. So now we can figure out our bonding. Bonding is now 3 with the 3 chlorines bonded to the iodine. There are 2 lone pairs on the center atom. So I think you can see the pattern. So far, all of these have steric number of 5. So it's electronic geometry. I'll just call it TBP, trigonal bipyramid. Okay, what is the molecular shape here? Now we're into uncharted territory. Let's look at our chart again. It's called T-shape. Let's take a shot at drawing this. So let me go back to my representation. So there's our trigonal bipyramid. Iodine sits in the center. Now, as we said, the lone pairs go into the equator. So we have 2 lone pairs at 2 of these positions. The third position will have a chlorine, and then the north pole and the south pole will have chlorine. So if you think about it, this is really sort of in the shape of a T. I mean, it's sideways, but it really forms a T shape. So that's where the term T shape comes from. It actually draws a T. Okay. So that's ICl3. Last one is xenon dichloride. Now that looks strange. One of the things you learned early in the semester is xenon has a full octet. It's very stable. You might have heard people say that it's unreactive because it has a filled octet. That's true. And for that reason, people really didn't think about xenon forming compounds, and they weren't discovered until the 1960s, which is relatively late in the chemical history. But it does form covalent compounds. Now, even though it's a filled octet, we're going to treat it just like anything else. Xenon is in group 8, so it brings 8 valence electrons. 2 chlorines, each bring 7, so that's 14. So this is going to be a 22 electron molecule. So let's draw the iodine in the center. Or no, not iodine, we're done with that. Let's put the xenon in the center. We put the iodines on the outside. 2 bonds. 2 bonds is worth 4 electrons, so we have 18 left to place. We'll put them 6 at a time on the 2 iodines. 6 and 6 is 12. So that means we have 6 left over. Those 6 will be put on the center atom as 3 lone pairs. And there we have our iodine, xenon. Whoops, it's not iodine, it's chlorine. I'm still stuck in the last problem with iodine. So we can just put chlorine here. And now we're talking about the right molecule. Okay, so let's go to our B and L. Bonding, we have 2, the 2 chlorines. L, we have 3 lone pairs. So once again, we have a fourth molecule which has steric number 3, electronic geometry of trigonal bipyramid. And let's do this shape representation over here. Xenon's in the center. We have 3 lone pairs. And remember, we said lone pairs go in the plane, in the trigonal plane. The chlorines will go north and south. So if you think about it, this molecule is just a straight line from the bottom chlorine through the xenon center to the top chlorine. So the molecular shape is linear. Okay. All right. Well, hopefully you're still with me. Let's see where we are. So we have completed the 5 a priori. So we only have 3 problems left. I'm going to keep going. Problem number 6, electronegativity trends and bond polarity in chapter 8. Okay. So this is I'm sure you feel at this point of the semester it's really a challenge. The topics are coming fast and furious and everything is happening at warp speed. Okay, so let's move over to problem 6 on your list, which is chapter 8, problem 831. And let me try to summarize what that problem is. It actually gets into electronegativity. And it says, without using the electronegativity table in figure 8.3, predict the order of increasing electronegativity in the groups of atoms. So they want us to predict increasing electronegativity. And I'll write the groups. So we have A, which is C, N, and O. B is S, SE, and Cl. C is SiGe, and Sn and D is Tl, S, and Ge. Okay, so let's summarize these. Let's put the lowest electronegativity here. Let's put the highest here and fill these in. Okay, so if you have a periodic table handy, we'll try to work these trends out. So carbon, nitrogen, and oxygen, these are all in the second row. And as you know, electronegativity increases as you go left to right. So the lowest will be carbon, the highest will be oxygen, and that puts nitrogen in the middle. Okay, the next grouping is sulfur, selenium, and chlorine. Well, chlorine and sulfur are on row 3. Chlorine is to the right, sulfur is to the left. Selenium is in row 4. So that's going to make chlorine be the highest of all of them. Sulfur and selenium are in the same, they're in group 6, but sulfur's higher, selenium's lower. And as we said, electronegativity decreases as you go down. So that will make selenium the lowest, putting sulfur in the middle. Okay, the next grouping, silicon, germanium, and tin. If you're looking on your periodic table, those are all in group 4. And it's going to be pretty straightforward. Whichever one is highest in the group will have the highest electronegativity, and that will be silicon. Whichever is the farthest down, group 6, that will have the lowest. That's tin, and that puts germanium in the middle. Okay, the last one is thallium, sulfur, and germanium. Okay, so these are really moving around. Sulfur is in group 6, germanium group 4, and thallium in group 3. So we're kind of going on a diagonal across the periodic table. The highest will be sulfur. That's the highest row, and the farthest group to the right. The one that's going to be the lowest row and the lowest group is going to be the thallium. And again, germanium winds up being in the middle. Okay, that wasn't so bad. Okay, let's move on. The next problem in that grouping is 833. And the problem's a little similar. And what they want is, again, without using figure 8.3, using trends, predict which bonds will be the most polar. So now we're going to have pairs, and we're going to ask about polarity of the bonds. So what they're going to do is they're going to say, we're going to compare carbon-fluorine bond, a silicon-fluorine bond, and a germanium-fluorine bond. And let me write them all down, and then we'll go back and work them. Okay, so the next one we're asking SF, SCl, B, SBR. C is PCl and SCl, and the D is TiCl, SiCl, and GeCl. Okay, so we're really going to be working problems where we have an element bonded to one of the group 7 elements. Okay, let's look at the first grouping. Carbon, silicon, and germanium bonded to a fluorine. Whichever one has, fluorine of course has a very high electronegativity. Whichever of carbon, silicon, and germanium has the lowest electronegativity will have the most polar bond. So most polar bond, most polar bond means highest delta in electronegativity between atom 1 and atom 2. So the biggest difference will give us the most polar bond. Okay, so I'll go through this quickly. Carbon, silicon, and germanium are all in group 4. Germanium is the lowest in the group. That means it's going to have the lowest electronegativity. It will have the most polar bond. Okay, now what's common in B is sulfur is what's common, and what we're going to be bonded to is fluorine, chlorine, and bromine. Again, fluorine, chlorine, and bromine are all in group 7. Fluorine is the highest, and that will give us the largest delta. So the SF bond will be the most polar, because this will give us the greatest difference in electronegativity between the two atoms. Okay, third one is phosphorus chlorine versus sulfur chlorine. Phosphorus and sulfur are both in row 3, but sulfur is group 6, phosphorus is group 5. So phosphorus is farther away from chlorine. It will give a greater difference in electronegativity. It will have the most polar bond. Okay, now we have chlorine compounds with germanium, silicon, and titanium bonds. Germanium and silicon are both in group 4. Titanium is way, way over to the left in the transition series. And again, since it's far to the left in the periodic table, it will have the lowest electronegativity, and the difference will give it the most polar bond between it and chlorine. Okay, so that's problem 6. Okay, problem 7 I think is not from the book. Let's get back to the worksheet. And the question asks, arrange the following from highest wavelength to lowest wavelength. Infrared, X-ray, microwave, visible green, visible blue. Okay. So let's just write these down. Let me just write the type of radiation we're trying to evaluate. And this is covered actually in page 253. So let me just write them down. It's infrared, X-ray, microwave, visible green, and visible blue. If you flip to page 253 and look at that little chart, 253, and I'm just going to kind of read them off. So what you're going to find is the shortest wavelength is going to be the highest energy. The shortest wavelength is going to be X-ray. So that's going to be number 5. And let's identify the longest wavelength. Well, the longest wavelength is the lowest energy, and that is going to be the microwave. And then after that, in the visible spectrum, the next shortest, microwave is the longest, the next shortest will be infrared. And then we have to look at visible green and visible blue. If you look, green is slightly longer wavelength than blue, so green will be the third longest and blue will be the fourth longest. So green will be longer, blue is shorter, and then X-rays will have the shortest wavelength. So this is, so 1 equals longest wavelength. 5 equals shortest. Okay, almost done. Okay, let's look at the last problem. Formal charge. Oh wait, I just realized I forgot one problem. Going back here, we were going to work problem 123. I skipped that. So let's pick that up now. It's a Lewis structure. It's not a long problem. It's really pretty short, but it's a good thing. I don't want to skip it. 533. Or it's actually problem 833. I just looked in my notes and I realized we skipped past that one, so let's go pick that one up. Okay, so it is problem, in your textbook it's problem 123. So let me read it to you. The problem says, 123. Problem says, which of the molecules in exercise 119 are polar? Okay, so this is one where you have to go back. So what they want to ask is between SeO3 and SeO2, which are polar? So what we're going to have to do is determine the geometry of it. Now, what does polarity mean? So we have two types of molecules. We have polar and we have nonpolar. Let's start with nonpolar. Nonpolar molecules are ones which are symmetrical. Symmetrical molecules are ones where the electron density is distributed evenly throughout the molecule, so there's no buildup of excess electron density on one end or the other. So these are going to be nonpolar. A polar molecule is an asymmetrical molecule, and it's really just that simple. So what we need to do is draw the Lewis structure, determine the geometry, and then figure out which one are they symmetrical or asymmetrical, and determine the polarity. Okay, so let's start with SeO3. Go back to our rules. Selenium is 6. 3 oxygens is 3 times 6, which is 18. 24 electrons. Let's, selenium will go in the center. We'll put the 3 oxygens around the outside. The 3 bonds are worth 6. We have 18 electrons left. After we place the 18 electrons, we've run out. Now, this is the first example where they say draw multiple bonds if required to satisfy the octet on the center atom. Well, right now the selenium only has 6 electrons. So what we actually need to do is create a double bond. So let me do that over here. Okay, so let's add up our parameters, our bonding. How many outer atoms are bonded to the center atom? 3. How many lone pairs are on the center atom? 0. So the steric number is 3. Let me take you back to that chart. So this puts us in the steric number 3. And what you notice is if we have 3 atoms at each of the 3 positions, it's going to be trigonal planar. And that is going to be the structure of this SeO3. So this will be trigonal planar. Now, one has a double bond and the other are single bonds, and this gets to the topic of resonance. You can look in your book, and it basically says that that double bond is not localized on one selenium oxygen atom. It's actually distributed throughout. If you look at this molecule, because of the oxygens being at all 3 positions, the molecule is symmetrical. So it is nonpolar. Okay, let's quickly do SeO2. It's similar as selenium and oxygen. Selenium is 6. 2 oxygens will be 2 times 6, which is 12. So it's an 18 electron molecule. Selenium in the center, oxygens on the outside. Those 2 oxygens, the bonds contribute 4 electrons. There's 14 left over, 6 electrons on each oxygen. That's 12. We have 2 electrons left over, and as we saw several times, that winds up, that extra electrons wind up on the center atom as a lone pair. Now, once again, we only have 6 electrons on the selenium, so we need to create a double bond. Now, so what are our parameters bonding? We have 2 atoms bonded into the center. We have 1 lone pair, which gives us a steric number of 3. If we look at the chart, we're still in steric number 3, but now we have a bent molecule. Let me draw it a little differently. So it's still a triangular geometry for where the electrons are, but in one case we have a lone pair. In the other case, we have oxygens. And if you look at this molecule, if you think of a plane of symmetry going this way, it looks symmetrical. But if you look at a plane of symmetry going that way, we have a lone pair on one side of the selenium and an oxygen in the other. That makes this an asymmetrical molecule, which means it is polar. So SeO3, symmetrical, nonpolar. SeO2 is asymmetrical, and what drives the whole thing is the lone pair on that selenium atom. Okay, so that's the difference. Okay, let's move on to the last problem, which is going to be formal charges. This is the last topic we'll cover for the day. And let's see what the problem is. Problem 105. in Chapter 8. Okay, 8.105. So let me describe this problem. Let's see, where is it? Write Lewis structures that obey the octet rule for the following species. Assign the formal charges for each center atom. So there are A, B, C, D, E, F, G, H. But let's work three of them. Let's work A, B, and C. So the A and the B and the C are, in this case, POCl3. The B is perchlorate, ClO4 minus, and C is So2 Cl2. Okay, let me get my notes. All right. Now let's define formal charge. What does that mean? Formal charge starts with the Lewis structure, and it represents the electron density that resides on a particular atom. Now, in this problem, they want us to focus on the center atom only, so that simplifies it a little bit. So what is the way that we're going to calculate or come up with that formal charge? So let's put together a simple definition for it. And this is going to be the valence electrons that the atom originally had as the molecules are going to be formed, minus the number of bonds plus lone pair electrons on that atom. Okay, so let's just keep that in mind. Let's go off and build our first molecule. So let's start with POCl3. Phosphorus brings 5 valence electrons. Oxygen brings 6 valence electrons. 3 chlorines brings 3 times 7, which is 21 valence electrons, for a grand total of 32. Now, we have to select the center atom. Phosphorus is going to have a lower electronegativity than oxygen, so we'll put phosphorus in the center and put every other atom as an outer atom. 4 bonds represents 8 electrons. We have 24 left over, and we'll put those 24 around the outer atoms 6 at a time. Okay, so there we have it. So there's our structure. Now we're going to say the formal charge on phosphorus is going to be the valence electrons phosphorus originally brought. Phosphorus is in group 5, so that's going to be 5, minus the number of bonds that phosphorus is involved with in the molecule. Well, there's 4 bonds, and plus the lone pair of electrons. This is the lone pair of electrons that reside on phosphorus, and there's none. So the formal charge for phosphorus in this molecule will be +1, just 5 minus 4. So they aren't asking us to calculate formal charges for the other atoms, so we're just going to keep it simple. Okay, next one, perchlorate. This is a good example of bring something that we haven't encountered yet. Is a charged, a polyatomic ion. How do we deal with that? We follow the exact same rules. Chlorine brings 7 electrons. The 4 oxygens brings 4 times 6, which is 24 electrons. Oops, what happened? Okay, here we are. Okay. Let me get to the perchlorate. Okay, that brings 24, which is 31. Now, anytime you get an odd number, you have to give it some thought, because the problems we're going to work are always going to have even numbers. What does the minus mean on the perchlorate polyatomic anion? It means that there's 1 extra electron in the system. So we're actually working with a 32 electron system. Okay, chlorine we will put in the center. Okay, and again we have 4 bonds, 8, 24 left over, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, so there we have it. All our electrons are used up, so there's our perchlorate structure. Formal charge on the chlorine. So again, valence electrons, chlorine brought 7 to the molecule, minus the bonds, 1, 2, 3, 4 bonds, and the lone pair electrons on the chlorine, which is 0. So it's going to be 7 minus 4, which is plus 3. Okay, last one. So2 Cl2. Okay. And where do we have that one? Okay. So, sulfur is 6. 2 oxygens is 2 times 6 is 12. 2 chlorines is 2 times 7, which is 14. Add all those up, we get 32. We'll put sulfur in the middle and put all the atoms coming from as outer atoms. 4 bonds is 8 electrons, 24 left over. 6 apiece around the outer atoms. So the formal charge on the sulfur center atom is going to be 6, which is the valence electron sulfur brought to the molecule, minus the number of bonds, plus the number of lone pair electrons on the sulfur, which is 0. So that formal charge will be plus 2. And I think with that start, you can go off and work the other ones. There's a lot of replication, but I don't think it's necessary to work every single one. Okay, well, we've worked all the A problems, we've worked all the B problems. It's taken us a little over an hour and a half, so I appreciate you spending the time. Now, as we wrap up, I'll give you one more chance to ask any questions. Other than that, we're going to save this recording, and we'll be providing it to Dr. Kelley so she can then distribute it out to your class, so the other students that weren't here will have a chance to review it. So thanks again. I'll give you a minute if you want to ask any last questions, and then I'll turn the recording off. Okay, anything else? All right. All right, well,